Hello everyone. Today we will be discussing our approach to the current drug and substance abuse crisis. The first question asked us to find a model that predicts nicotine use through vaping over the course of the next 10 years. We define nicotine use as repeated usage of nicotine, otherwise known as nicotine addiction, and we did this in order to best utilize the data available for vaping currently. Our approach revolves around a susceptible infected model, and we utilize two different differential equations to represent the flow between the susceptible not addicted population and the infected addicted population. We also use Euler's method in order to represent change over time. So our first assumption is that every person has the same probability of addiction regardless of individual factors. We did this in order to standardize our model. Furthermore, populations are likely to even out over time. For example, younger populations will likely age out into adult populations over the course of 10 years. Furthermore, those that have previously been exposed to nicotine through other means, such as cigarettes, are still susceptible to vaping. Our second assumption is that addiction is not a spectrum. One can only be classified as not addicted or addicted, and we said this in order to divide our population into compartments for our model. Addiction is usually a definite term and not a vague one as well. Our final assumption is that the United States is representative of overall more economically developed countries in terms of nicotine use through vaping. And this is because vaping is generally more costly and therefore more prevalent in MEDC countries. And so the United States would be a good representative of nicotine use through vaping around the world.
So going into the model, here we have a list of all the variables that we use in our equation. You can see at the top we have two variables, S, which again represents the susceptible or not addicted population, and I, which represents the addicted population. We also have N, which is just the sum of these two values. Furthermore, we also have 5 different variables that are rates that are being used in our differential equations in order to calculate the change in these populations per year. So this is what our model is. These are the two differential equations. On the top, you can see this is the change per year of the susceptible population. On the bottom, this is the change per year of the infected population or addicted group. So breaking down the model a little bit, first we have our value alpha n, which represents the people who are being born into the model per year. For this value, we just use the US growth rate per year value of 0.7%, multiply that by the total population N in order to have the number of people that are being born into the unaddicted population. Our next variable is P, which represents sort of the incubation rate from the infected group from the susceptible group into the infected group. In terms of real life application, what this represents is the kind of natural decay or natural rate that people are trying these drugs without significant influence of peer pressure. And so we found this value online to be 1.4%. One unique thing about our model is that it's different than current SI models in the sense that in an SI model, if there's a negative interaction, the person is immediately moved over to the infected population. However, in our model, a negative interaction is defined as only one use of the drug, and so we don't actually. There's a certain probability associated with becoming addicted, so there's not an immediate chance. That's why we multiplied these variables by 30%. The last variable in our equation is gamma, which represents the negative interaction rate between the susceptible and the infected populations. In terms of the actual model, in terms of real life, this represents the kind of influence of peer pressure and the growing popularity of this dangerous drug. And so, unfortunately, this is a very new sort of epidemic, and we don't have a lot of information regarding it. So we estimate its value to be between 5% and 35%, choosing a value of 20%, which is just the average for our actual model. So here you can see that we applied this value over, this is all 3 versions of the same graph. We can see there's been over time, there will be a net decrease in the susceptible users, and there will be an accelerating increase in the addicted users. So another part of the question asks us to compare this model with cigarette usage, and so we found out that pretty much over the past 58 years there's been a 28% decrease in the total population in terms of cigarette usage. So using these values, we created a linear equation, and we could see that just under 8 years seems to be the point where the nicotine vaping usage surpasses that of cigarettes. So with the sensitivity analysis, like I said before, our gamma variable was estimated, and so we could see that there is a significant difference between our lower and upper bounds, and so it does indicate potential error in our model. However, there are many strengths of this model. One of the strengths being the fact that it's very robust in its application. This means that if you want to change some of the parameters, it's very easy to do so. Furthermore, this model has also potential to be optimized through a deep learning method. If you have the data and not the parameters, a parameter fitting procedure can be used to find out what those parameters are that will minimize the cost from the true value of the data. Additionally, this model is also very good for adding compartments. For example, if we wanted to more accurately reflect the total population, we would add our R group, which could stand for recovery, and this would represent kind of people who have recovered from the infection, and so from the addiction. And so this would help, we could have its own interaction rates, and this would help further make our model more accurate. However, one of the weaknesses of the current model is the fact that there is currently no way of removing people from the I infected group. However, we did this because there's not a large amount of data regarding this online. However, in the future, if we wanted to extend upon this, we could create another variable, omega, which could represent the incubation rate from the infected population into the susceptible group.
Okay, so in the second problem, we were asked to determine the number of high school seniors out of a class of 300 that would use alcohol, unprescribed opioids, nicotine, or marijuana during their senior year. So to do so, we had to determine the likelihood an individual would use a drug based on their characteristics, such as race or gender. And in this problem, we define drug usage as the likelihood an individual uses a drug at least once, drug usage as using a drug at least once during a year. To highlight our main assumptions, so first of all, we assume that race and gender distributions in high school are the same as in the entire United States population. So as a corollary to this, we assume that the 300 high school students that we specifically considered have a distribution of traits that is the same as the entire United States. So for example, there would be 49% of students that are white. Finally, we assume that income can measure socioeconomic status. So there are a lot of measures of socioeconomic status, but drug use trends are largely the same across all of them. So we chose income as our representative measure. In developing our model makes use of a weighted average calculation to determine the likelihood an individual uses a drug. So to define our variables, P represents the probability a person with a trait uses the drug, R represents the range of probabilities of a trait, and then W represents the weight given to a factor. All of these probabilities of use are per year because our model determines the likelihood a person uses a drug within a year. The three factors that we specifically consider in our model are race, gender, and socioeconomic status, but these are used as representative factors. We acknowledge that other factors are important and could easily be added to our model given more time and data access. To calculate the weight given to a trait, we divide the range of probabilities of the trait by the total range of all of the probabilities of traits considered. So we use range as a measure of variability, and our reasoning is that variability can determine the relative importance of a factor. So for example, if the probability of use of nicotine is the same for all races, likely race is not an important factor to consider. However, if one race is 50 percentage points more likely than another to use nicotine, then likely race would be an important factor. The individual's final probability is calculated with a basic weighted average calculation where the weight of the trait is multiplied by their individual probability based on a specific trait. So to do an example calculation, we can calculate the weight of race and nicotine usage. So we divide the weight of the range of race by the sum of the range of race, gender, and socioeconomic status to give us our weight value of 0.456. We can then use this value to calculate, for example, the likelihood a white male of high socioeconomic status uses nicotine during his senior year. So here we multiply the weight of race by the likelihood a white person uses nicotine. We add that to the weight of gender multiplied by the likelihood a male uses nicotine, and so on, to give us our final value that there's a 15% chance that this individual will use nicotine during his senior year.
Okay, so in order to apply our model, we developed a fairly simple Python program which simulated 300 individual high school students, each with 3 different characteristics: race, gender, and socioeconomic status. So for each of these characteristics, we assigned them a different variation, and we did so using this data shown below in the tables. So for example, given a random high school student, there is a 26% chance that they're Hispanic or Latino, 50% chance that they're male, and a 50% chance of them being of high socioeconomic status. So we can multiply all of these values together to get 6.5% chance of this student having all three of these characteristics. Note, we are assuming independence between the different factors here, and I will touch more upon that later. So as a result, after running the simulation 5 different times to account for 1,500 different students, we took the averages of all of our simulations and compared it to accepted values given by the NIDA. So as you can see, our values for nicotine and marijuana are fairly close to the accepted value, while our value for alcohol is a bit further off. And note, we did not have an accepted value for opioids since it's such a recent crisis, and there was not enough data on the internet about opioids used by high school seniors or younger people. So to conduct our sensitivity analysis, we first looked at age versus total population. So on the table to the right, you could see a table of nicotine use for population from 12 to 17 and the general population and all of these characteristics. So when we compared the 12 to 17-year-olds, which is the data that we used for our model because it was the closest we could find to high school seniors, with the total population, we see that the values do not differ by much, which means our model is not very sensitive, and it could be applied to the general population if necessary. We also took a look at income as a marker for socioeconomic status. Data online has showed that income is as good as a marker for socioeconomic status as any other marker. So this makes our model not very sensitive as well if we decided to use other markers. So our biggest strength for our model is that our model is extremely flexible. It's easy to add in different factors such as mental health, such as drug abuse programs and grades and more to our model to account for even more factors that would make our model even more accurate. However, our biggest weakness is that we do not account for the lack of independence between the different variables. We acknowledge the fact that sometimes different characteristics are correlated with one another, but we did not account for that in our model. So our biggest extension for our model would be to incorporate some type of factor analysis that would take a look at all of these different factors and account for the dependence between them. This would make our model much more accurate and much more robust for the future.
In problem 3, ripples, we examined marijuana, opioids, alcohol, and nicotine in order to rank them according to their negative impacts on a society. In order to do this, we made the assumptions that different factors could be directly compared so long as they were weighted appropriately, with weights being determined by each factor's impact on life. Next, we assumed that different economic burdens would have similar impacts and could be grouped together, with the reasoning that no matter the source of the economic burden, which in our data involved the cost of healthcare, lost productivity, addiction treatment, and criminal justice involvement, would be used towards the same purposes had the money not been lost because of a drug. Along with economic burdens, we also took into account the deaths per year, the number of users 18 and above, as well as the number of users 12 through 17. We took these 4 factors and weighted them in our ranking equation in order to determine a score for each drug, with the proportion of each factor of each drug being weighted with a weight of 0.5 for every trait, excluding the number of users above 18. Our reasoning for this was that many of the users 12 through 17 would go on to use a drug once they moved into the 18 plus age group, and we did not want to overcount the number of users as a factor in our model. A table of values as well as a sample calculation for nicotine shows how we obtain each score by simply obtaining data values and plugging them into our equation. For nicotine, this results in a score of 0.777, making it our most harmful drug, followed by alcohol, opioids, and marijuana. You can see from our ranking how our ranking can reflect different kinds of traits. For specifically, opioids and marijuana have somewhat similar scores despite their large differences in impacts, with the note being that marijuana has 0 deaths per year but a larger number of users, whereas opioids has fewer users but a higher economic burden and more deaths per year. Our strengths of our model is that more factors can easily be added, no matter the magnitude or unit, because of our proportion system, and because of this, different factors are easily compared. However, a limitation of our ranking is that it is made with only US data and as such might not reflect global trends. In the future, we could use global data in order to create a global ranking. Finally, we have no specific formula to determine precise weights of additional factors, and because of this, we must research each new factor appropriately, which concludes our presentation. Thank you for your time. We'll be now taking questions.
Thank you. Also, congratulations. Wonderful job. First question. Let's see. On page 21 of your presentation, you talked about calculating a probability using the sum, but you had weights based on the range. The thing that you're calculating there, how do you know that that's a probability or makes a probability distribution?
Do you want to go look? Maybe they pulled the slide up.
You can, yeah, if you feel more comfortable.
Specifically, because the ranges will always sum to 1 for everything, because each one is a proportion of the total range of everything. So the ranges and the portion, the variability in the range sums to 1, and because of that, it functions as weights as it should, and because it's multiplied by probability, it's essentially averaging them.
I also have a question about weights, but the weights for question 3. So I'm just wondering how you determined, you mentioned a little bit about just the difference in the weights, why one of them is 0.2 while the other are 0.5, but how did you determine 0.5 and 0.2 to be the weights there?
The exact numbers for our weights in this model don't mean anything specifically. Rather, the ratio of the weights to each other indicate how much significance we place on each. Because of the limited time span we had, we took each trait that we considered, aside from the number of users above 18, to be roughly equal in importance. Which is why and 0.5 was chosen as a somewhat arbitrary number, and then 0.2 as just a number that is less than. And because of that, our weights are somewhat crude, admittedly.
I had a question about the third question. You were simulating all for you. You were simulating the high school students, and I think you said you ran your simulation 5 times, or is this question 2?
This is question 2, yes.
Sorry. So you ran it 5 times.
Yes.
Given time, running it 5 times is totally appropriate, but if you had more time, what would be an appropriate number of times to run the code, or how would you know what the right number, what would be a good number?
Well, a good number would be if we ran it, let's say 50 or 100 times, the results that should be produced should average out by the time that we get to 50 or 100 simulations, because that's basically how statistics works. Since when you take different probabilities and you keep running simulations, it will eventually average out to the probabilities, the final probabilities that it should be. So it rules out all extraneous, just extraneous. It rules out all the event chance things that might happen to influence the data.
So this is also about question 2, and just a more general observation that we saw when we were reading papers was that few teams incorporated that role of social influence, particularly peer pressure. So maybe could you just comment a little bit about how your team interpreted what the challenge question was asking in that regards, and why?
Well, essentially, for our problem, we only wanted to show how it could be done. So the factors that we specifically considered were meant as representative factors. We recognize that there are a lot of other important social factors, but it's harder to find data on it, especially in a limited period of time. And because of that, we focused instead on showing how we could use this model to account for these things as long as we had enough research and data to do so.
I'd like to go back to question 1. You talked about approximating your system using an Euler approximation. Could you discuss that and talk about that and maybe explain how you might make a better approximation?
Yeah, so we basically ran this model using Euler's method, and so we started off with the initial population, and so every single year you saw the two differential equations that were being used, and so this model, using those differential equations and there's values, we have every single value plugged in, so we have a rate of change that occurs based on the total populations of the different compartments. And so this was our way of effectively using of finding out what it is. But again, like could be better ways of doing it. Just maybe you could take instead of using a compartmentalizing model, there's potential to be using a statistical model instead that similarly measures kind of like different population growth values instead. So rather than differential equation, we'd be using a value not in terms of change and just in terms of the population itself. So.
Thanks, congratulations, you guys did great.
Thank you so much.